James Webb is really cool, man. Like, I mean, the main goal, the main objective for this telescope is mainly just to look at the, as you were saying, like those OG stars. Let me say that, the
Yeah.
OG galaxies. You know, like those moments right after the Big Bang is really what it's trying to is it really what it's trying to look at, and we can, I mean, hypothetically, we can really understand a lot more of the universe's starting point with this telescope. Because even though the Big Bang is a widely accepted theory,
Hmm.
it's still just that. It's still just a theory, right? So, like,
Yeah.
there's still no, it's not the Big Bang law. It's not the law of the Big Bang or something like that, right? So it's still being theorized. It's still being updated. Like, what are the specifics here and there? And this can just give
Which is
us
at the same
a good
time, it is
understanding of that.
kind of a guess. The like here the thing is, we'll never be able to confirm one hundred
I mean, yeah,
percent
obviously, because we weren't there.
I know. That's the fun part
But
though. It's like
obviously.
we have this evidence, like we have the CMB that we can look at. We can send really expensive telescopes to go look at it. And it's like, okay, the fact that we see the cosmic microwave background radiation, it has these properties and it looks like this, and we have a certain method to date things. We can make conclusions where it's like, this is a possible way that it could have happened, that now, billions of years later, we see these consequences. At the end of the day, the universe could have been made up last Thursday. That was a funny
I
thing that we
love that
talked
theory.
about.
Last
That was a
Thursdaysm.
that was a
I
funny
love that. I
thing we
absolutely
talked
love
about.
that. So,
Yeah.
quick update before we get into the pyramids. Just quick little run through I do want to do for some big events this year. So in 2021, especially in physics, we had two major breakthroughs in the world of physics, and those are two specific experiments: the muon G-2 experiment, and then I don't know if this experiment has a formal name, but a theoretical time crystal. So the muon G-2, we actually had a really cool episode on that with Don Lincoln from Fermilab, the guy who literally runs the laboratory. So definitely go check that episode out. He actually talks intensively about the muon G-2 experiment itself, what it means, why it's important, and why it basically shatters what we understand. But quick rundown I'm going to give you guys. So the idea is that all these particles, these fundamental particles, have some idea of spin, of quantum mechanical spin that we understand. We've spoken about multiple times on the podcast. And when you put an external magnetic field on these particles, they basically start to wobble around, or they basically start to wobble in this thing. And the amount of wobble, or the magnetic wobble, is referred to as the G factor. And
Oh,
all
it's
particles
actually
have a,
interesting.
yeah.
In one of my problem sets, it was like an extra problem that wasn't graded, but I did it. And actually, what we did is
Of course you did.
we calculated what happens if you put like a particle that has a certain spin in a constant magnetic field that points in one single direction.
Oh,
And so
really?
I actually solved myself and saw that like the expectation value for the the components of the spin, like the one that's in the direction of the magnetic field doesn't change, but the ones that are perpendicular to the magnetic field actually precess at a rate that is like directly related to the strength of the magnetic field. And so the stronger the magnetic field is, the faster the spin precesses around the axis that the magnetic field points in.
Well, that's
Yeah.
interesting to know. That's actually really cool
Yeah.
that you actually did a
So that has
problem
to
on
do with
something
like,
like
the
this.
wobble of the
Yeah.
of
That's
the
actually really
particles.
cool. So yeah, so that's
Yeah.
basically the inherent G factor, like an intrinsic magnetic compass almost. Because remember, they have their own compass, and you're putting an external compass. You're like, how much does it wobble? So that's the G factor, and the standard model of particle physics predicts G factors for all the particles, right? Like that's the whole point of the standard model. However, with a recent experiment a couple years back, they did it on the muon, and they found that the experimental results were about 3 sigma away from the standard model predictions. Now, sigma means standard deviations, and in like an experimentalist term, 5 standard deviations is significant enough to qualify for a new theory. So that's basically the idea.
5 is a lot though.
Five,
Like,
yeah. So 5 standard
like
deviations is enough to almost like solidify that a new theory is required or something
yeah.
is being misunderstood. So that was about 3, 2.7, 2.6. It was something like that. And then they're like, oh my, let's just do it again. So then Fermilab comes up and does it again. And this happened this year where they did it and they got a result that was almost 4.8 sigma
Damn.
away from the standard model. So this is literally almost calling for a new theory, or we're just not understanding something about the original one. So again, we have one of two options. Either we're adding a particle, some other hidden particle is acting that we're not understanding, or we're not understanding the original already existing particles, which is
Yeah.
a really cool theory. And I think
Yeah,
on the
that was
episode
really cool.
itself, on the episode itself with Don Lincoln, he was talking about how right now we can't really tell if that's the answer, but they are doing significant experimentation. And I think he said like next year or by the year after, we would know if whether or not the model itself was incorrect. Because I believe he
I'm
explained,
actually
he did something. He said something. Just go check out the episode.